Hello, everybody. Quentin Morris here. I'm a solutions architect on the aerospace and satellite team, and I'm fortunate enough to work with Skywatch, a exciting venture-funded startup in the Earth observation data delivery space. And with that being said, I would like to introduce you all to the image processing and machine learning lead at Skywatch, Alexander D'Souza.
Thanks very much. Thanks very much, Quentin. So let me tell you a little bit about Skywatch, what we do, and how we're trying to reduce EO data volumes and really optimize costs for satellite operators. So what is Skywatch? So, on the back of winning the NASA Space Apps Challenge in 2014, Skywatch was founded as a company that looked out into space, actually, to measure supernovas. We pivoted to Earth observation in 2016 with a goal of democratizing Earth observation data so that users could get around often the large order prices that were needed to be able to bring this data in from large providers. Now, we've been pretty successful with that, and in 2021, we received our Series B funding. So let me show you kind of the imagery that we deliver, typically. So this is the kind of imagery you might expect from Skywatch. This is 50-centimeter data, courtesy of Airbus, and it looks great, right? You can see really clearly what's in it, airplanes, a number of other vehicles in there. If you squint a little bit, you might even be able to make out some of the numbers of the runways. There's a lot of latent information in this kind of image. But there's a lot of complexity involved in being able to acquire this. The path from when the satellite actually captures it to how this data is processed and delivered can be lengthy and complex. There are artifacts that often need to be corrected and a host of additional processing that I'll touch on briefly. And whether it's monitoring an airfield like this or monitoring areas for climate change and seeing the effects of that on the area, being able to reliably access data like this is critical for a variety of applications. But there's a perennial problem that plagues Earth observation, and that's that at any given time, roughly 70% of the Earth is occulted by clouds, right? So that means we have customers and satellite operators who are paying to navigate a satellite over a particular area of the Earth, open an aperture, capture an image. They have to downlink the imagery and the data, which only happens over discrete points around the world. A bunch of processing goes into correcting artifacts, fixing the image. It's delivered to the customer who's eagerly anticipating it, and it's completely cloudy. There's no usable data available in that image. So at Skywatch, we're really working on ways in which we can save those costs and higher up the funnel determine whether or not we can prevent delivery of bad imagery that way, both to avoid having to downlink it for the provider and ultimately the delivery of bad imagery to customers. So ideally, you want to be able to intercept those kinds of images, right? If you have a scene on the left, you immediately reject it. And a scene on the right, there's usable information, you can deliver that to the customer. So I'm going to dive a little technically right now, because at Skywatch, what we've done to overcome this is we've developed a state-of-the-art machine learning model. For those who are technically inclined, I'll dive deeply into it a little bit. It's basically the backbone of this is a UNet type of architecture with a ResNet encoder decoder. For the encoder and decoder, we've used ResNet 50 here, and that's pre-trained on ImageNet. So, you even heard in Werner's talk, you don't need to train models from scratch. If you can leverage models that exist, expert models, ImageNet itself is based on 14 million images, so we use that as kind of the backbone for the encoder and decoder there. But of course, to develop an expert model, you can't rely on 14 million images that were trained on ImageNet because cats, dogs, and cars do not look like clouds. So at Skywatch, what we've done is also built up what we now believe is one of the largest available data sets for manually annotated cloud imagery. And that's been able to allow us to build and deploy a really sophisticated algorithm that's agnostic to sensors and also resolution, so that really any provider can take advantage of this kind of model. So let me show you how that works, how we develop this. Underlying all of it is a slew of serverless components, whether it's code images through ECR, step functions and lambdas that do the orchestration for the training, SageMaker, obviously, for the training as well. We build those artifacts up, and we deploy them serverlessly as well, so that we can have what we call a live model that's running in production. And as our engineers make further changes and improvements to those models, the data set's improved, we can deploy as many shadow models as we want alongside that. So all of the images that come in can be simultaneously processed through those models with SageMaker, have all of those inferences collected in buckets in S3, and we can do an investigation into which models are performing best, and then perhaps replace them in production as well. And so on the far left, you can see a little bit of comparisons of some of the imagery, and I'll show you some more of those in the demo portion in a little bit. So this has been really successful for us in reducing those costs, because now we can help suppliers of this data really intercept it before it gets to customers. Now, our model is, so everybody's probably familiar with like ChatGPT. So if you aren't familiar with that, that's an enormous model. That's what they call an ensemble expert model. It's basically composed of like 5 models that are each a few hundred billion parameters. This is a really fine-tuned expert model. It's only 11 million parameters, so it's 5 to 6 orders of magnitude smaller. But we're not trying to do everything with it. We have it fine-tuned for a very specific task. Even still, this thing is a few hundred megabytes in size, and so pushing it into space is really difficult. Because that's what we're trying to do at Skywatch. Reducing these costs on the ground is one thing, but we really see a next evolution where we can push critical classification tasks like this directly onto satellites in orbit, in space. Doing that allows us to be able to, allows providers to capture imagery, do all the processing, classification, and if a piece of image is bad, they don't even need to bother with downlinking that and doing any additional processing. But of course, to do that, we need to scale these models tremendously. And so we've been thinking really critically about how we take the lessons we've learned from building the types of serverless architectures that we have on Earth with AWS, and how we do that in space as well. And a core component of that is really separating the critical ground infrastructure from the space-based infrastructure as well. So that again, in space, whether it's cloud detection or object detection or what have you, we can really just turn on and off the specific components that we have to do. All right, so let me show you a demonstration of the model and how it works, and I'll show you a little bit of the size as well. All right, so yesterday I was looking, this is a Skywatch platform. Yesterday I was looking for a piece of imagery. I wanted to show something from Las Vegas while we're all here, but unfortunately for the demo, the weather has been beautiful. Where it has not been beautiful is Canada, which is where Skywatch is based. We're in a city called Waterloo, just outside of Toronto. And it's been snowing tremendously. So yesterday I downlinked this piece of imagery, so it's very recent, and I'll show you a little bit what it looks like. It looks like this. So this is a great example of how our model will run. I'll show you, this is the actual image. I'll show the model outputs in a sec. You have clouds and a completely snow-covered field. So detecting clouds over a nice forest or a piece of mountain is one thing. Detecting it over snowed areas is another entirely. Now, on the spacecraft itself, we have a Docker container. This contains a lot of the critical infrastructure for running the systems for the satellite, communication with the sensors, as well as the model infrastructure as well. It's 3 gigabytes, but remember that is actually going to be on the hardware when the satellite is launched into space. When you need to communicate with the satellite and push new model artifacts up, our actual model I'll just show you a few checkpoints in here, are only 22 megabytes here for our TF Lite version. And let me show you the outputs then. So I have the Docker containers all pre-built. I'm just going to set one running. And then I'm going to do, I'll do the execution. And so this is, I'll do our HDF5 one first. Oh. All right. So it's just going to do a little bit of TensorFlow, what TensorFlow does best, but the inference times are really quick here. So 2 seconds to be able to get the inference out. And I'll show you the kind of fidelity that we're able to get. So here is, is this it? So this is the original image. And then this is the model output. All right. And if I can do them a little bit side by side here. So you can actually see the output of the model is just a latent pixel map, but it not only detects the clouds and where they are, it is able to detect the degree of occultation by the clouds, the density. Now this is the full several hundred megabyte model, right? If we do the same evaluation now with a highly compressed model instead, so this model takes a little bit longer to execute, and by a little bit longer, I mean like 3 seconds instead of 2 seconds. And that's because the model is compressed itself, so the imagery has an additional compression step to be able to run through the model. And so this is the TF Lite output. And so you lose a little bit of the detail because you have to compress the image for the compressed model, but you can still see that the output perfectly captures the clouded area. All right? And so now from space, we can actually do highly accurate pixel maps, completely reducing the amount of costs and the operational flows that satellite providers need to be able to deliver this kind of imagery to the ground. All right. So, yeah, thank you very much for your time. And if you have any questions.